Pavutnitskiy, who will talk today about the work of a group in our industrial projects on Quadric hypersurface intersection for manifold learning in feature space. Without further ado, Fedor, please.
Okay, yes, greetings everyone. As Slava mentioned, although I'm presenting this work, actually it was a work of a group of people in industrial projects. And first of all, I want to say big thanks to these people, to Slava Borovitsky, to Sergey Ivanov, Zhenya Abramov, Vitya Vyalov, Artyom Klachkov, Tolik Zaykovsky. All of them are my colleagues, so we work on this together. And at the end, I will share the screen with the paper. If there will be any questions, right, I will refer to the paper and you will see them in the title in orders. So yes, as Slava mentioned, this was our project for the last year in St. Petersburg State University and Huawei Joint Lab. So Huawei, I will just give a very, very brief abstract. Huawei asked us to try to apply some geometric or topological methods to anomaly detection for embeddings of the face recognition system. I will explain all the terms in the talk. So this is a result of our project. We indeed construct some manifold model for these embeddings and use it to do some anomaly detection. Just in case, yeah, this is the overview of the talk. So first, very shortly, I will talk about manifold learning in general. What is the manifold? What is the manifold learning, etc., etc., etc. In the second part, I will describe our manifold model, which is based on quadrics, zero set of quadratic polynomials. And the third part, we will talk about application of this model, the main experiment in face recognition system. Okay, what is a manifold? Of course, everything that I will be talking about here is very, very informal. I will not give any strict definition, and I'm sure you're familiar with them. This is just to refresh some geometric intuitive definitions for people who are not working in geometry or topology. So think about n-dimensional manifold as a geometric object that locally looks like Euclidean space, right? So elements of this manifold of this space is not exactly vectors of a vector space, but locally it looks like vectors. Locally this space looks like Euclidean space, and this is all we need to do. So how to formalize this locality? So it means that, as I wrote here, yeah, sometimes I will be rid of slides, sometimes I will just speak. So in the end, I will share the slides. So in some sense, they're self-contained. It means that for any point, we have some neighborhood that is homeomorphic to some Euclidean space. So this neighborhood called a chart, and in general, manifold can be covered by a few charts, and they have intersections between them, and this intersection should be compatible in a certain way. But what is important, again, informally, how to think about charts is just a way how to provide coordinates for points. So although the points on the manifold are not vectors, locally, we can think about them as vectors. And what do we mean by think about them? Means we provide new coordinates for these points. So it is important to notice that in this definition, there is no mention of some ambient space where manifold is embedded. So manifold itself is a space, and it is not necessary that the manifold we're talking about is embedded anywhere. And for some manifold, for example, as I wrote here, for torus, there are a few very familiar embeddings, right? We know that two-dimensional torus can be embedded in three-dimensional vector space, but the canonical embedding is in four-dimensional Euclidean space. Other examples of manifolds, which are, I'm sure, familiar to you, is the vector space itself, right? So it can be covered just by one chart, the space itself. Sphere, right? We need two charts to cover it. And which will be important for our talk today is some zero sets of some function. Of course, we need some conditions on the function if we want nice manifold, but we will not be bothered with these conditions today. This was about manifold. What's a manifold learning? So suppose we have some point cloud in Euclidean space of dimension d. I will be referring to this point cloud as a data set, as a finite subset of Euclidean space. This is, but speaking from more machine learning perspective, we will think about this as a data set, because usually in industrial matters, in applied matters, we think we get our data sets as collections of vectors. We present our data as collection of vectors, right? But what do we mean by manifold learning? Again, this is informal definition, so I will not speak about manifold hypothesis here. It have it can be formulated strictly, but for this talk, I will take it out of scope. So by manifold learning, we mean that some collection of techniques or algorithms for describing geometric structure that is underlying X. So what I mean here is that we believe that if our data set, our data have all points of our data have the same nature. For example, all of them are images of dogs, right? So we encode our images as vectors, right? And all of them are images of dogs, say, for example. So we believe that this nature of the data can be encoded using geometric terms. So in speaking more strictly, we assume that our points are not only vectors of Euclidean space, ambient space, but they have an additional structure, and they actually lie on some manifold. And all, in this example, all pictures of the dog lies on the same manifold. So there is some geometric structure, the manifold, that describes the manifold of pictures of the images of the dog in some ambient space of whole pictures, of all pictures. So, and we believe that this, of course, it's just one possible way to describe this inner nature of the data. Another way is to use some statistical terms, some distributions. For this talk, we'll be taking a geometric perspective. And in manifold learning, we believe that this geometric description capture the interdependencies between points, the underlying structure of X better than just a collection of vectors. So structure of X as a collection of vectors is insufficient for us to work with this data set. This is some application scenarios of manifold learning. So what manifold learning is used to. So first, I will give 4 examples. Only 2 will be relevant for us. But this example is not really relevant, but still, this is actually one of the most often application of manifold learning. This is a data visualization. So we have a collection of vectors in a very high dimensional Euclidean space, right? For example, I don't know, space of pictures, right? For example, MNIST, you know, this is a data set of handwritten numbers, right? Digits. And so each picture is 28 to 28 pixels, something like this, right? And we have each digit, handwritten digit, is represented by a vector of dimension of few hundreds, right? So how to visualize this data, how to understand it? This is where manifold learning come to rescue. So manifold learning here is used as a dimension reduction algorithm. So we try to find a manifold, in this case of dimension 2. So try to find the coordinates, just 2 coordinates that not explain but visualize our data in a meaningful way. So it can be seen here that using this manifold learning algorithm, UMAP, this is very popular for visualization now. We can actually see that after we project our data to 2-dimensional Euclidean space or find a 2-dimensional manifold that fits our data, we can see that actually we found some clusters of data, right? And each cluster actually represents a digit. So it will be very hard to find this clustering in 700-dimensional space, at least visualize it. But in 2-dimension, it's very easy to grasp it. Another relevant application is data interpretation. We tried not only to reduce the dimension of the data to better visualize it, we tried to find some meaning of these coordinates, right? For example, in this picture, the data is images of 3D model of human head with different lighting direction and different poses. So algorithm that is used here is ISOMAP. This is very, very famous algorithm from the 2001, I believe, beginning of 2000s. So in this case, the dimension was reduced to 3. So in their work, they fitted a 3-dimensional manifold. They found a 3-dimensional manifold that fits the data. And so it needs only 3 numbers to express each point, each image. And it turns out that actually every one of these 3 numbers, every one of these coordinates has a meaning. So as you can see here, one of the coordinates is posed from left to right here. Another one is posed from up to down. And the third coordinate is represented by a slider here. It's a lightning direction. So this way, of course, data interpretation is much more powerful than just visualization, because we can see what can we change in data so the data will change in a predictable way. So this is really important. But for us, the most interesting application will be an anomaly detection. So let's return for a bit to a manifold of the images of dogs or face embeddings or anything. So if we found such a manifold that actually every point of this origin of image of the dog, say, lie on this manifold, we can easily use in the ambient space, we can easily use this for outlier detection, right? Because if now we get another point, which is not an image of dog or say face, then we just need to measure the distance from this point to the manifold. And if the distance is big, then this is possibly an outlier. Of course, usually it's impossible to fit like all the points, right? So all the points of the data set that you have will lie on the found manifold. Even if you get this, usually it's overfitting, right? So of course there will be some tolerance. So points will be not like exactly on the manifold, but will be close to it. So the distance to the manifold can be, if it's given with the embedding to the ambient space, then the distance can be used as some sort of outlier score for the point. And actually, this is what we've done in this talk. Last application scenario that we'll cover today is metric learning. Again, we haven't done it properly in full generality, but we have some very, very rudimentary metric learning that I will show later. But in general, idea is the following: that again, if we found our desired manifold that geometrically express the nature of the data, then similarity between different points, or dissimilarity, so how much the points is different, is much more natural to measure along the manifold, right? And not in the ambient space, because as it's shown here, if the manifold embedded very non-trivially in the ambient space, then the Euclidean distance in the ambient space can be not very good measure of the similarity of the points by nature, right? So these points are quite different, but actually distance between them is quite small. So if we work with these points just as a vectors, we see two vectors that are very close to each other, and we think, well, the images that are represented by these vectors are also quite close, which is not true. So in this case, it is better to use geometric distance on a manifold. So in this picture, Euclidean distance is small, but geometric distance is quite large, which better represents our idea that the corresponding images are actually quite different. Okay, this was an application scenarios. So what have we done in our project? It's called out-of-distribution detection based on structure and dimensionality learning by topology analysis. This is the original name. So as I said in the beginning, idea was to apply this anomaly detection method using the manifold learning algorithm, submanifold learning algorithm, to anomaly detection in feature space of face recognition system. So idea is the following. I will return to it later in the experiment section, but for now I will just say a couple of words about it for better understanding. So idea is the following. Instead of working with pictures of human faces, it is more efficient to construct what is called an embedding of this image to train some deep model, so convolutional neural network, for example, to produce a vector of lower dimension, right? Because if you have a picture in 3 colors of 100 by 100 pixels, it will be 30,000 dimensions, right? It's too much. So we need to reduce this dimension somehow, and in the same time found the representation which have the desired properties. So convolutional, deep convolutional neural networks is used for this task. And in the end of this network, for each image, one vectors, in our case, it have dimension 512. One vector of lower dimension will be constructed. And usually all the manipulation, classification, identification, these things are done on top of this, what is called phase embeddings. So idea was to use manifold learning techniques in this 512 dimensional space. In particular, our partners were interested in anomaly detection in this space. So we try to use manifold learning for anomaly detection in this feature space. So the first question, how to represent the manifold such that it will be most suitable for this problem? Because as I told you before, manifold is something that looks locally like Euclidean space, and this locality is incorporated in charts. There may be a few charts, transition functions between them. This is complicated. Is it really suitable for our problem? So yeah, this is what I try to explain. So for a few charts, if the manifold is covered by a few charts, there need to be some transition maps between them to ensure that actually points in the intersection of the charts have compatible coordinates in these charts and this chart. And actually, at least I don't know the manifold learning algorithm that implement this structure in full generality, right? So it can be very tricky to put the idea of the manifold in the computer in this exact form. So typically, manifold learning algorithms works just with a single chart. So how the manifold is represented in the computer, right? In this manifold learning framework, it is just a function from our set of vectors to some Euclidean space of lower dimension, typically lower dimension k, right? So it can be some metrics, for example. So this is very simple representation of a manifold, and the cons are the following. The pros are the following. First pros. Of course, if you have a chart, means you have a new coordinates. So you have an explicit description of new coordinates for our data set. So for every point, you can find new coordinates that express this point on the manifold in the chart. So it's very suitable, quite suitable to visualization and interpretation. And again, if we know that locally our manifold looks like Euclidean space in some small neighborhood of each point, actually Euclidean-based distance can be a good approximation of geodesic distance. Of course, it may be non-true without the word locally, but nevertheless, in some neighborhoods it's possible. Cons are the following. Of course, we limit quite severely our class of manifolds that we considered. We only consider a manifold that can be covered by one chart. For example, torus cannot be covered by one chart, right? Sphere cannot be covered by one chart, etc. So sometimes there are also, for example, in the map, there is some condition of this chart that it should be isometric. So if you cannot have weird things with curvature, for example. So it is another limitation. The chart itself doesn't provide any embedding of the manifold to the ambient Euclidean space, right? It goes just in this direction, not in another one. So from what I want to say, that from new coordinates, you cannot get the old coordinates. So at least for now, it's unclear how to use this model for anomaly detection in the previous sense, when we need to measure the distance to the manifold from some ambient point. And this is about particular realization of some algorithms. Typically, it is sometimes impossible to project new points for the manifold. So suppose you have some data set, you feed a manifold to it, right? And now you have a new point, and you want to, that this, even if you know that this point is on the manifold, right? You want to find new coordinates for this point. Usually it is impossible to do so without retraining the whole model. So you need to find a new manifold that includes these points. And of course, it makes sense in some sense, because if the points is far from manifold, you can know it beforehand. Sometimes it will be impossible to project it on the manifold, how to say, injectively, not injectively. I forgot the word in English. The word in English, that doesn't matter. So it is natural that sometimes it's impossible to project new points without retraining the model. So since at least at the first glance it's unclear how to use it for anomaly detection, we use another representation of a manifold. This is a representation of the manifold as some zero set of some function, right? So actually any manifold with any manifold can be represented as a zero set of some function, right? For example, if you already have a manifold, just consider the following function, the distance from a point to the manifold. So of course, for all points of the manifold, this function is zero, right? And only for this point. So any manifold can be represented as a zero set of some function. And actually, as you can see, if we describe a zero set of some function, we don't have any new coordinates. We work in the old coordinates. So this manifold, in some sense, described in the ambient space already. So of course, we don't have in strict sense, we don't have this embedding, right? So the way how to go from new coordinates to old coordinates to the coordinates to ambient space, in ambient space. But it's, as we will see below, it's not necessary actually. The cons are the following, that as I mentioned, there is no general way how to obtain these coordinates on the manifold. So it's not very usable for interpretation or visualization. And actually, if we are interested in metric learning, of course, it depends on the function f, but it can be very hard to compute a geodesic distance on this manifold. Okay. Yep. This was about the manifold learning in general, about our initial problem and how we try to choose the appropriate model for this problem.
Sorry, Fedor, can I ask a question?
Sure.
So if you don't have a coordinate system on your manifold, what is a geodesic distance? So if you don't have a metric defined, how do you define geodesic distance?
Exactly. If you want to find geodesic distance, first straightforward way is to find some coordinates on this manifold. But for example, let me try to think. It is possible to do, I think it is possible to do so without charts, but I just recall that in isomap algorithm, what is actually happening first, some k nearest neighbors graph is computed for your data set, and then the geodesic distance is computed, approximation to the distance is computed by shortest distance on this graph, right?
So you assume that metric is somehow the same as
locally, yes.
Hausdorff metric, right? So it's just a metric of ambient space.
In isomap, yes, that's why it's called isometric mapping, right? So actually, locally, you don't bend the space too much. So in this algorithm, yes. So I want to say that in some case it's possible, but in full generality, of course, you need coordinates. Yeah. Okay.
Yeah. Okay.
So, okay. We for the problem of anomaly detection, we choose the following function. We choose the representation of the manifold of a zero set of some function, and the function is the following. We choose our d minus k dimensional function. D minus k is because our manifold will be of dimension k. We choose this zero set as an intersection of zero sets of some quadratic polynomials, or what is another way how to call it, quadric hypersurface, or just quadric. in short. So our function will be a tuple of quadratic polynomials, and zero set of this function will be intersection of the zero sets of each of the quadrics. And as I wrote here, in non-degenerate case, there is another thing, what's exactly mean by non-degenerate, but in non-degenerate case, this will be described a k-dimensional manifold embedded in our original d-dimensional space, Euclidean space. So a couple of words about how to present this. In general, quadratic polynomial, this is a bit obvious, but still. So any quadratic polynomial can be presented as in this form. You have some bilinear form on X with some matrix A, symmetric matrix. Some this is like quadratic part, quadratic monomials. Then multiplication by some row vector and some free term. In how to say, not in a matrix form, but in coordinates, we will write it down like this. We will need it, I believe, couple of times in the talk, but still, we will use both of these forms for quadratic polynomial. Yeah, and how to switch between these forms is just symmetrization. These are just a few examples.
Fedor, may
Sure.
I interrupt to the previous slide?
Yeah.
Yes, so the typical dimension, as I remember, is 500.
Yes.
Yes. So then the space of parameters, yes, as I see it here, is 25,000 around this.
I think even more. It depends on number of columns. Yeah. Okay.
Yes,
okay.
yes,
For
yes,
one.
yes, 250,000. Yes, and as far as I understand, in order to reduce, say, from 500 to 400, you will need so 2 million parameters.
The model have not millions parameters, less. Okay, first of all, it's not 250,000, but half of that because the matrix A is symmetric, right?
Okay.
So half of it, and this is actually for one quadrix, yes, and after we have a few of them.
Yes, and in order to go from 500 to 400, you need 100 of quadrics.
Yes. Yes.
Okay.
So this is okay. I understand. This is very interesting actually. So it's a bit controversial, at least for me. So in some sense, I will try to explain. The more quadrics we have, the smaller manifold we get in the end, right? But the more quadrics we have, the more parameters we will have. So in our case, the bigger the dimension of the manifold is better because we have less coefficients.
No,
right?
but this is normal, because if you go from 5, like in order to describe very tiny curve, you need the one.
Of course, yeah. To find a curve that fits like all the data, go through all points. Yeah, of course, we need many parameters. Sure. What I wanted to say is that when we discuss it and try another manifold learning algorithms, our idea was to find a manifold of as low a dimension of possible, right? Because we have the huge space R in 512, right? And we have very particular manifold, the manifold of embeddings of human faces, right? So we suppose that dimension is actually quite small, so say twice of this. Twice as low, for example, 200 or even 100. So we try, at the beginning, we try to find the manifold of lower dimension. But after that, we understand that actually from computational point of view, it's better to, dimension doesn't mean much here. The number of parameters is more important. So yeah, thanks for the question.
Yeah, and another question, yes, is like for me, it's not clear, but do you have something like universality theorem, something like any manifold can be well approximated by something of this quadric?
We don't We don't have this, but Mumford have this.
Okay, it will be, okay, yeah. So
yeah, actually, it's from algebraic geometry. So Mumford says something along this line, that every projective algebraic variety is isomorphic to intersection of quadrics. So in some sense, it's, at least in my head, it is similar to kernel PCA, right? When you have some manifold, very, very complex one, and you project it in infinite dimensional space, that actually you can find maybe linear manifold, right? That is very close to it. So at least I understand the theorem of Mumford in the same way, right? What he do, he take projective algebraic variety and embed it in the high dimensional projective space, and there it can be found. It can be described as intersection of quadrics. So in this sense, yes, quadrics are actually quite expressive objects. It is actually quite funny that another object from topology, moment angle complexes, I learned it just yesterday from my colleague, is also represented as an intersection of quadrics of a special type. And this moment angle complex can have very complicated topology actually. So contrast to the linear model, this intersection of quadrics are quite expressive. So already in dimension 3, this is just a few pictures, you can see that they can be disconnected. They not necessarily are simply connected, so they can have complex topology. Okay.
Excuse me, I want to mention something. Just that I suggest taking this universality with a grain of salt, because this only concerns topological structure, not metric structure. So this isomorphism of algebraic varieties is something closer to diffeomorphism than to isometry. And actually, we are more interested in metric properties. So
no, but I'm sorry, Slava, can you be more precise? You speak diffeomorphism, homeomorphism.
If I remember correctly, it's about diffeomorphisms.
No, because if it's a diffeomorphism, it at least preserves the notion tends how it preserves much more about.
Yeah, I understand, but we would like ultimately to preserve metric structure, and it doesn't do this at all. So
but with metric structure there is no hope. There you only can say that locally you can approximate by quadrics, because in any case quadrics are something is an object of finite dimension. Yes, yes, and then how to say, you have only finite dimensional space of manifolds. Yes, and for sure, how to say, if you want to consider manifolds up to isometry, there should be, how to say, infinite dimensional space of them, so that there is no chances for them to be.
Well, the interesting thing is that the more traditional ways of manifold learning through neural networks, they assume one chart representation, and what they end up with is the situation where they seek a diffeomorphism of basically Euclidean space into a curve, one charted manifold, and what they're interested in is actually only how this changes metric structure. So like mainline manifold learning through neural networks is all about this metric structure without disregarding topology. But what we are talking here is more like thinking about topology and less thinking about metric structure, although it's actually quite important.
No, but we preserve very important notion of tangent distance to zero. So on a certain level, on some level of how to say, not mathematical rigorously, yes, things. So we still keep understanding, is the distance between something is small or large. Yes, if we consider only kind of small and large, then we preserve this notion.
Okay, I will intervene for a moment for what is actually important in this mode, that we can compare it to the points in the ambient space. So indeed, we are not really interested in the metric per se on the manifold, right? So we are not really interested in the metric learning by definition, right? What is the nice notion of the metric between points, or how to find a manifold that preserve this metric, right? As Slava mentioned, what is done in neural network approach, or how this metric changes, right, in the new coordinates. Why this model was chosen? It's because it is possible to find this model is naturally embedded in the ambient space, and it is possible to find the distance to the manifold. So we are not really interested in the geodesic distance or metric inside the manifold, but we're interested in, okay, metric is a not correct word here. We're interested in the distance between the manifold and the points in the ambient space, points that are not belong to the manifold. So this is the idea behind the choice of this model. Okay. Let's move further. By the way, when should we finish? How much time do I have?
Usually we have 1 hour and a half, so it's like
1.5, so till 5 p.m. Okay.
Yeah.
Okay. So yeah, then I will start with the analogy with the linear model. So PCA, principal component analysis, can be thought as also as a manifold learning algorithm, which just find a linear manifold that fits data the best. So I wouldn't recall the whole algorithm. I hope you're familiar with it. But what I want to say that actually the principal component analysis can be thought as an algorithm that finds a zero set of a certain function, a function which is a tuple of these inner products, where these vectors are eigenvectors that found by PCA. Again, what I wanted to say that the mean squared error optimal linear manifold of dimension, say, k, that is found by PCA, this one. So each point here is a linear combination of the PCA eigenvectors. This hyperplane, this plane, k-dimensional plane, can be expressed as a zero set of this function, right? So this is a plane which is orthogonal to all other eigenvectors, which form the basis of the space. So now, after we understand how we will present the model, how after we have a particular choice of the function by quadratic polynomials, how to find the coefficients of this quadratic polynomial, how to fit the manifold to data. Again, we will build off of the linear model, so we will try to understand how PCA works and try to get this intuition to the Quadric model. So in PCA model, what is actually happening? Of course, you can reformulate it more conveniently into some eigenvector, eigenvalue problems, but actually what happens, you, during fitting the linear manifold, you try to minimize square of geometric distance from your points to the linear manifold that you found. So you define a function like this. So before V was the eigenvectors, so solutions exactly. These are just the vectors that you optimize, right? So you have d minus k vectors, and you minimize over the coordinates with some constraints, which are orthonormality of this vector. So they should be orthogonal, and norm of each vector is equal to 1. So this is how you can reformulate PCA algorithm as in a more geometric terms. And this interpretation is beneficial for us because now we can switch this linear function by our function defined by quadratic polynomials and try to solve this problem. So if you forget PCA here, this is actually optimization problem that we try to solve. So for zero set of some quadratic polynomials, we try to minimize the square distance from points of our data set to the manifold, to the zero set of our function. But actually, it turns out that it's very, very hard problem. So I recall the geometric distance is defined as some infimum So as Euclidean distance from the point to the closest point on the manifold, right? And depends on the manifold in general, it can be very hard computationally. From computational point of view, it can be a very hard problem. So we need some approximation of this geometric distance function. And in this paper, of course, at the end, there will be a lot of references. So as I said before, the slides are self-contained, so you can refer to them later if you want. So in this paper, a series of approximations of geometric distance function was introduced for in case when your manifold is a zero set of some function. And there is a series of this approximation, in some sense, based on the Taylor formula, Taylor expansion. We, for quadrics, because you have only polynomials of degree 2, so there are no third derivatives, etc., only 3 of them are relevant. Approximation of degree 0, 1, and 2. So first obvious approximation is just an algebraic distance. So in some sense, it's a very crude approximation, right? So for some function, you can very roughly approximate distance from any point as just a value of this function on the point. So on zero set, this distance is 0, right? Away from zero set, it can be arbitrary, right? But actually, for a linear model, it's not hard to show that this distance coincides with geometric distance. And this is actually why it is possible to solve this problem in case of PCA, right? Because actually this geometric distance in the linear case is easier to compute, and you can reformulate this problem as an eigenvalue eigenvectors problem. This is approximation of order 0. Also, another maybe familiar to some of you, approximation of order 1. This is just an algebraic distance divided by a norm of the gradient. But this is good, but not good enough for us. So the next approximation is approximation of order 2, which we will call 2 distance. It have this maybe complicated, but not actually so complicated formula. It also involves algebraic distance. It also involves some norm of gradient. And it also involves something that is called a Hilbert-Schmidt norm of your function. Or in case of quadric, I believe this formula is true for quadrics. I should mention it here. So this formula works for when f is some quadratic polynomial. So in a moment, I will describe what is a Hilbert-Schmidt norm. We introduce it here just because it looks neatly with this notion. So, and this 2 distance is our choice of approximation of geometric distance. So advantages are the following. In contrast to algebraic distance and to distance of order 2, distance of order 1, sorry. Distance of order 2 is majorized by geometric distance. It facilitates robustness in the following sense. So if you remember the formula for D1, this one. So in this formula, you divide by a norm of the gradient, right? So if in some point your gradient is equal to 0 or close to 0, this will be a huge number, right? So this is not happening for approximation of order 2. So it's actually always lower than geometric distances. So we don't have a huge values here. And during gradient descent, you will not have any problems if you go to regions where distance of order 1 is big. Another very important observation that actually distance of order 2 and also this distance of order 1 also have this property. But still it's invariant under the action of Euclidean group. So for any isometry, distance between the point and on the manifold doesn't change under this isometry. What do I mean here by this? It means that when we fit a manifold, you have some point cloud in the ambient space, right? And when you found a manifold that fits this cloud, so you want to find a manifold such that your points lies close to this manifold. You want by this manifold, you want to capture some geometric properties of the data, right? Which in some sense depends only on the inner distances between points. So if you rotate the cloud, right, you should find a rotated manifold, right? If you if you translate the cloud by some vector, you will find a translated manifold. This is a natural geometric property that we want to assume from our model. And actually for algebraic distance, this is not working. I will show you in a moment why it fails on the illustration. But for now, let's keep in mind that this invariance under the action of Euclidean group, so invariance under rotations and translation, is very important for our manifold model. Now let's switch to the optimization constraints. So let's recall that in linear case, we have some orthonormality constraints on coefficients, right? Let me try to, yeah, let's go here. So we need some constraints on coefficients of this vector, such that, for example, that we will not have, say, all coefficients are equal to 0. So this distance is 0 for all points, and we found a trivial solution, right? We want to exclude, for example, trivial solution. That's why we put these constraints on the norm of the vector. And if we want to exclude some linear dependence, we also put an orthogonality constraint. Yeah. Of course, we want to do the same for quadratic polynomials. So we want to exclude trivial case, because in this case, the distance will be 0 and we will have trivial solution. And because linear quadrics that are linear dependent, if coefficients of quadrics are linear dependent, then the intersection of these quadrics will have the same 0 set. Intersection of the 0 sets are the same. It doesn't change under with the linear dependence of the coefficients. So we also want to exclude this. So how to introduce these orthogonality constraints into the optimization? There are obvious way to do this the same way as we done in linear case. Let's just ask for all coefficients to be orthogonal in the following sense. So for each quadric, right, we can consider a vector of its coefficients. So it have this dimension. So this is the dimension of quadratic part, right? Number of quadratic coefficients before quadratic monomials. Then you have linear part, right? Coefficients before linear monomials, and you have free term. So for every quadric, we can from every quadric we can get this vector of its coefficient. So we can introduce orthonormality constraints as orthonormality constraints on these vectors, right? So during our optimization, we will ask that inner product of these quadrics is 0 if quadrics are different. But turns out this is not actually a good constraint because it is not invariant under the action of Euclidean group. So this is the illustration that I wanted to show. So in this example, we have 8 points on the plane, right? And we want to fit one quadric, and we want to find one quadric that fits data the best. Yeah, sorry. Okay. So what's orthonormality constraints means here? We don't have a few quadrics, so we don't need to bother with orthogonality, but we want the norm of our quadric is equal to 1. So in this case, only the condition of a norm is our optimization constraint. And it turns out that this condition doesn't hold if we switch our quadric. Yeah, I'm sorry, I will try to switch. Yeah, sorry. Okay. Yeah, it's very, very hard to speak in English and hear the vacuum cleaner. It's okay. Okay, what's happening here that actually you see the same point cloud but shifted by some vector. And after we try to feed the manifold with the same constraints, with the same optimization problem, we actually found that it's not an optimal manifold, right? So it's not invariant on the not invariant on the translations. Okay, this is what we want to avoid. So these constraints of the full orthonormality on the vectors of coefficients is not suitable for us. We need to find another optimization constraint. And this is where Hilbert-Schmidt norm come to play. So instead of considering the vector of whole coefficients of each quadric, we want to consider a vector of its quadratic coefficients. also with some multipliers, so some rescaling on the non-diagonal entries. So we consider only the vector of quadratic coefficients, and let's define the Hilbert-Schmidt product, inner product of the quadrics, just as a scalar products of this quadratic part. And the corresponding norm, it's actually a semi-norm, is defined in the usual way as we define norm from inner product. I call it semi-norm because you see it depends only on quadratic part. So if your quadric have a trivial quadratic part, right? So it doesn't have quadratic part at all. It have only linear part. Then its norm will be 0, or because it doesn't, all these coefficients will be 0, but the quadric itself will be non-trivial. In matrix form, it have much neater formula. So if, let me try to, to return here. So let's recall that each quadratic polynomial can be written in the following form, right? Some quadratic part represented by some matrix, a linear part, and free term, right? So about this quadratic part, so Hilbert-Schmidt product here can be expressed using this quadratic part. So it's just a dot product of quadratic part considered as vectors, right? So it can be represented as a trace. And if you actually look closer on this formula, you can see that this is the reason why this inner product is equivariant with respect to, it means invariant under the action of rotations, orthogonal group, and translations. Because how to prove this? Basically, you just try to understand how this isometries, this Euclidean group action, acts on the quadratic part, and you will find out that action is actually just how to call it in English, conjugacy, сопряжение. Is it conjugate by matrix, right? I forgot the word, sorry. So the action here is just a conjugation by some orthogonal matrix, right? And of course, trace is invariant under this action. Okay. Finally, the loss function that we minimize, or in other words, our optimization problem that we try to solve. So this is just the loss function, how we write it in the computer and use gradient descent. So in this loss function, the first part, this sum, is an approximation of the distance to the zero set of quadratic polynomials, intersection of zero sets of the quadrics, intersection of quadrics. Yeah. So approximation is actually like two-step approximation. First of all, we approximate the distance to intersection as sum of distances to single quadrics. This is the first step. The second step, we switch from geometric distance to distance of order 2. And if you recall the case of PCA, in PCA, we actually minimize the square distance. Here, we choose the absolute value instead of square, like L1 approximation, just to increase robustness, right? Because lower powers grow slowly than higher powers when you go away from the manifold. This is about the main term, right? But now we need somehow to incorporate constraints. And our Hilbert-Schmidt orthonormality constraints. We use this just by regularization. We try different methods like optimization on Stiefel manifold, optimization on a product of manifolds, but we found out that actually just a soft usual regularization works the best. So this term ensures that actually our quadrics remain orthonormal with respect to Hilbert-Schmidt inner product. Yeah, and we just use the stochastic gradient descent to minimize this function. Okay, I believe, to example. Yeah, finally, some pictures of quadrics. So this is a toy experiment that we performed just to check that our choice of approximation of geometric distance function is indeed facilitate robustness. First of all, we took tennis ball curve, right? It's a curve that you found on a tennis ball, right? It's actually a curve of order 6, right? We sample some points on this curve and add Gaussian noise to it. After that, we try to find our manifold that fits this data as an intersection of two quadrics. And we've done it in two ways. First, we use algebraic distance, and after we use two distance. So these are two different approximations of the distance. Yeah, I forgot one thing. We also add this arrow. We also add an outlier of norm 2, so to check how it's how the model is how the model reacts to outliers. And it's actually easy to see from the picture that if using an algebraic distance, which is actually nice, it's fast and it's easy to interpret in terms of kernel PCA, but it's not really robust, right? So it reacts to outliers very strongly. But our two distance approximation it actually doesn't feel outlier much. So the curve is quite close to the original one. So this is just
very impressive.
Thank you. Yes, this is nice.
Can you explain why it doesn't feel outlier? Is it evident?
This one is one evidence. Okay. At least it shows why it's better than D1, than approximation of order 1. Another evidence is that actually algebraic distance is it's not distance at all, right? The only common thing with that it have with distance that it's 0 on our manifold, right? So if the point x lies on a 0 set of function f, then of course this algebraic distance is 0. What happens outside of the manifold? It can be anything, right? So it depends on the function. That it's actually very hard to predict. But on another point of view, if we use algebraic distance, the whole problem of finding quadrics can be reformulated as actually linear model, but in some high dimensional space, in space of coefficients of quadrics. So it's with algebraic distance, it's some sort of kernel PCA. So it has some advantages, such as if it's kernel PCA, it can be solved as an eigenvalue problem, right? So it's fast, etc., etc., etc. But in this particular project, we were mostly interested in robustness of the model. That's why we decided not to use algebraic distance. Also, it has some advantages. Yeah. Okay, so this is just an illustration. There will be more illustration, but later. Yeah. Okay, a couple more formulas. So in the beginning of talk, I mentioned that we want to use this quadrics model for auto-distribution detection or anomaly detection, outlier detection. It's all the same. So we introduced the following outlier score. This is just the mean distance to quadrics, right? So this before this was our approximation to the geometric distance. So the only difference is this term. So this is our outlier scores. So we measure outlierness of the point just by an approximation to geometric distance to our manifold. And also, if we have some, this is an element of metric learning that I try to avoid in full generality. So somehow we want to, you will see later why it's relevant. Suppose you have some notion of similarity between your points, right? And if your points contain outliers or anomalies, actually this notion of similarity can behave quite badly. We will see some examples. So we try to robustify it in some sense. So to introduce our outlier score in this similarity function, so it works better when you have some anomaly problems. We done very, very similar thresholding in the following sense. So you choose some threshold parameter, and if your outlier scores are lower than this parameter, then you assume that your points x and y are normal in distribution points, and similarity between them just your normal similarity. But if you found out that actually one of the points is outlier, you just put the similarity is equal to 0, right? So you like don't want to consider these points at all. This anomaly points is different from all points. Okay. This was the whole description of the model and its application that we done. Let's move to the experiments. Okay.
Yes.
So I will very briefly try to explain about the experimental setting. So we consider the face recognition pipeline that have face detection, face alignment, deep feature extractor, and some classificator. On top of this, I will explain these notions. We choose the state-of-the-art model ArcFace with MCCNN face detector. And this model was originally trained on a data set of 6 million images of human faces. And as I mentioned before, dimension of the resulting face embedding is 512. And we use actually the embedding of this training data set to train our Quadric model. So this is what I feel I need to explain. So what is the face recognition system? How it typically works? So it used to mostly solve the following problem. You have, for example, two photos of human faces. You want to understand, is it the same person or not? How to do this? Or, for example, you have some database of users, right? And you have a picture, and you want to understand what is the identity on this picture, on this image. How to solve this problem using some deep models. First of all, you need to recognize, you need to understand, is there really a face on the picture? So you need to detect the face. It may be I don't know, picture of with some backgrounds with a few faces. So you need to find the relevant one. So step 0 is face detection. After that, after you recognize that it's really a face here, you need to align it properly. So typically there are a few alignment points. So eyes should be at certain points, nose should be at certain points. This is a pre-processing step, which makes life easier for a next deep model. So this is done usually by a very, very simple neural network. I don't know, this MTCNN detection that I mentioned, I believe have 3 layers of something like this. So this is not really a deep model. A deep model starts here. So after you have aligned faces, this is an image of, say, 100 to 100 pixels. So it is a vector of dimension 10,000. I take colors out of considerations. So you have a very high dimensional vector. You want to reduce the dimension of this vector in a meaningful way. So this is what feature extractor do. This is a deep convolutional neural network. I will show an example in the next slide. And in the end of this network, you will have what is called a feature vector. So it is a vector of lower dimension, such that each coordinate is considered as some feature of the original image. So of course, these features are not really interpretable for humans, but the extractor works in a way that they're usable for the task that system should solve, for example, to identification, right, or to verification. So after you have this feature vector, now if you have a few feature vector, now you can compare them, right? So now if this model trained properly, if you have 2 vectors that are close to each other, then you believe that they actually represent the same person. So this is what's called feature matching, right? So usually it's done using cosine similarity function. So on the pairs, you can consider just a cosine distance, right? Cosine similarity between feature vectors and use it as a measure of likeliness of the vectors. So after you have this notion of similarity, now you can build a classifier on top of this, just all the technical stuff that is usually done. Let's see on the next slide. And after that, you can use this feature representation to identify the face on the original image. In our case, we work with the ArcFace model. So ArcFace model is trained in the following way. This picture from original ArcFace paper. So I will not explain all of the details. I believe it's not necessary. Just to have some pictures in the presentation, in slides. So idea is the following. So this deep ArcFace model is trained in a way that pictures of the same identity are, the corresponding feature vectors are close to each other, and the vectors of different identities are far from each other with some margin. So everything is happened on a sphere, right? So we work with the normed embeddings. So it's actually not in the whole 512 dimensional space, but on 511 dimensional sphere in this space. So everything have, we see normalization here. Everything have norm 1. So on this sphere, in the beginning of the training, for each image, the system gives just a random vector on the sphere, right? But during training, the optimization, the loss function is designed in a way that it penalizes, let's say better, it tries to reduce the angular distance between images embeddings of the same class, of the same identity, and try to make angular distance as far as possible for embeddings of a different classes. I'm not sure that I explained it properly, but nevertheless, this is just some cleverly designed deep recognition system that works actually quite well. So that's why it's the paper of 2018, and it's still, I believe, state of the art in face recognition. Anyway,
yeah, you would like here to replace a sphere by a torus, yes?
Yeah. This is what is possible to do. So they work on sphere, but it may not necessarily be a sphere. We can actually try any manifold and see what happens. Yeah. Okay, so this was our setup. So we used the embeddings of this ArcFace model. What tests do we perform? How to check that actually our found manifold works well? We use we perform two experiments and two different types of experiments, and measure two metrics. First experiment is just an outlier detection experiment, and another one is identification experiment. So in the first experiment, this is just normal anomaly detection, right? So you have normal points, in distribution points, and anomaly points, out of distribution points. You need to detect all out of distribution points. So this is a binary classification task, right? So you can use any relevant metric to measure the performance of the classifier. We use area under the ROC curve in this case. Identification task is what I tried to explain a few minutes later, right? When you have two images or two embeddings, and you need to understand, is it the embedding of the image of the same person? So in this experiment, as a metric, we use what is called an identification rate. If time permits, I will try to explain what is it. And we compare our model to the linear one, to the PCA, with the same ideas, right? You try to fit a linear manifold to your data. You try to measure the distance to the linear manifold. Use this distance as an outlier score, right? And also you try to incorporate this distance in a similarity function. And what is interesting, we use an anomaly detector based on the embedding norm. So it is very interesting that in face recognition, for some mysterious reason, norms of the embeddings of this one. So after the feature extraction, you have feature vectors, right? And they have some norms. Even though during training you work with the normed embeddings, in the end, on the inference, it may not be, the norm should not be, not necessarily should be equal to 1, right? And for some mysterious reason, I don't know if anybody knows why exactly, this norm of the embedding encodes some information about outlierness of the photos. So in this area in face recognition, there is some very strong baseline that we comparing with. So for outlier detection, we use the following data set. So how we construct this data set with anomalies. We take just one of the usual face recognition data set, MS1M, VGG phase 2, etc. Doesn't matter. And we add 1% of outliers to this data set. And outliers are the following. So it's partially pictures of low quality, pictures of different faces on one photos, and on another half, it's just anima faces. So these are examples of our outliers, right? So this photo is okay, but there is 2 people, right? So it's actually considered for us as an outlier, right? We don't know which identity on this photo. Photos of very low quality, right? Very hard to recognize. Photos in helmets, again, multiple people, and also some anima faces. There is, yeah, this is interesting. There is a special, I give a link here. This is a special dataset, anima face dataset. It contains about 60,000 images, right? And if you put these images in the pipeline here, right? You just put the anima face here. Actually, 10% of these images passed through face detection. So the natural question that one can ask about all this idea, right? Why to do anomaly detection on this step? If you want to detect some outliers, right? If you want to detect images that are not images of human faces in this face recognition setup using some manifold learning, why work here, not here? You have a face detection, right? This is exactly what face detector do, right? It detects faces. If there is no face on the image, then it will be just rejected. Turns out, no. For anima faces dataset, 10% of these images passes through face detection. And also face detection in some complicated cases works negatively in the sense that it can reject the photo with a human face on it. So it depends. Actually, this is not a really reliable detector. Yeah, these are examples of our outliers, and these are the results. So we mix these outliers to each of the data set. After that, we use our model. So here, okay, I will explain in a moment. So we mix these outliers to the data set, and we use various manifolds model detectors and detector based on norms. So here, I believe there are 300 quadrics. Here it's 100 quadrics, but they perform almost the same actually. So let's for simplicity, let's think that it's like 100 quadrics in general. What's D2 and D-alg means here? So both models were trained using this approximation of order 2. So as we saw at toy example, it's very, very important for robustness. But after the model is trained, since D2 have a complicated formula, right? It can be computationally expensive to compute in terms of time. Not very, but comparing to algebraic distance, the question can be asked, maybe after training using this one, we can use an algebraic distance. It turns out, yes, we can. And actually the results are very, very close. So again, both models here were trained using distance of order 2, but on inference, this one here, algebraic distance, was used as a distance to the already trained manifold. And here, distance of order 2 was used as a distance to the manifold. Okay. So in this experiment, Quadrics outperforms linear method, outperform norms by quite a bit. And actually, it works quite well as a detector. I want to mention that actually it really depends on all steps of the face recognition system. It not only depends on the deep model, so on the embeddings that were our training data set, but it also depends on the alignment procedure on the detector. So for some alignment procedure, norms works better. For some, they works worse. So it depends. It's actually a complicated matter. Norms are actually quite mysterious one. And yeah, let's look at this picture. So these are just example of outliers that were detected by various detectors. So these are outliers that were detected by Quadrics. This one were detected by PCA. This one were detected by norms. And it's funny that actually these are just 3 images from 64 images with highest algebraic score. So we just, for each detector, we took 64 images with the bigger score and take 3 of them. Just manually select like more representative one. So you can see that actually Quadric detects, for example, pictures, right, which are not photos of humans. It detects pictures of multiple faces, low quality. Quadrics also detects them, but surprisingly, it detects completely normal images, right? If time permits, in the end, I will show you like 64 of these images, but I don't think that time will permit. We have only 10 minutes left. For PCA, the situation is different. So majority of these outliers, so there's only 3 of them, but majority of the 64 outliers have huge sunglasses, right? So if there are no eyes on the picture, PCA detected as an outlier. Also, I forgot how to call it in English, like profile. Okay, that doesn't matter. So like side pictures are also detected as an outliers in case of PCA. Yeah, about identification. So yeah, here I sketched an algorithm what is an identification rate, but I believe I should just leave about 5 minutes on questions. So I think I will just explain it very, very briefly without details. So basically you have a similarity function between, you want to understand is to, you want to build a classifier on top of the pairs of the embeddings, right? So you use just cosine similarity and classifier based on this. So if your embeddings, 2 of your embeddings are close in terms of this angular distance, in terms of cosine similarity with some threshold, then you declare them positive. But that's not all. We also use what is called a set of distractors. So you take another data set, which have different identities, right? And you say that your pair is distracted, cannot be distracted. If similarity, if 2 elements of the pair are so similar that similarity is so big that it's bigger than similarity to all of the distractors, right? Distractors are different data set. In ideal situation, it shouldn't contain any identities from X. So this is an additional step in this algorithm that is really important. And that true positive rate of the corresponding classifier, it is what is called an identification rate. These details are not really important. This is just some, I don't know, procedure that is used in industry. I will also skip this. It will take more time to explain. That's the matter. Yeah, this is a result of identification rate experiments, which are quite surprising. So without robustification, you have like 60% of successful identification. Both Quadrics and norms are increased this by 4%. It doesn't look like much, but actually if you include distractors here, the increase will be high, like about 11%. For people in industry, it's like what they're aiming for. And actually PCA also performed quite well. So in some sense, any robustification method, so by robustification method, I mean this, this one. By robustification method, I mean this one. Try to thresholding the similarity if one of the points have a big outlier score. So it turns out Actually, any robustification method works quite well. The difference is 1%. In this strict protocol, it's important, but in the relaxed protocol with destructors and negative pairs, it's smaller. Yeah, these are results for this identification experiment. So both quadrics and norms are perform equally well, but also quadrics performs quite well in outlier detection, which was our main goal. Yeah, conclusions. As I mentioned, quadric models works quite well both in outlier detection and in the robustification problem. Again, this is not a metric learning. We're not trying to find a better similarity function. We just try to exclude outliers from the computation of similarity. Yes, it's improved the PCA baseline quite sufficiently in anomaly detection problem and by 1% in similarity robustification problem, but still. Norm-based baseline is indeed a stronger competitor. It has the same result in identification rate, but not so strong in anomaly detection because it's unclear how it's work. It's just empirical knowledge in this specific area, right? But our algorithm Quadrics, it actually doesn't depend on the particular deep model, right? It can be applied. It's not necessary even to apply it in a feature space. Why we done it here is, apart from the consideration that it was like an operation project, idea is the following, that usually if you Google manifold learning algorithm, you will find isomap, Laplacian eigenmaps, locally linear embeddings, nice stuff. But you will see that it scales very poorly with the number of the points if you have k nearest neighbor based algorithm, or it scales very poorly with the dimension. So if you Google manifold learning and you go to the pictures, you will see all the same pictures in 3 dimensions. Oh, we done something in 3 dimensions, which is also nice. It's also important, but of course it's much more useful to have an algorithm that works in quite high dimension, in orders of hundreds, right? And which can be scalable with the millions of points. So this is what our algorithm solves. And
yes, a short comment. Yes,
yeah.
So I asked before about universality of these quadrics. Yes, in dimension 3, it's actually clear that there are not so many of them. Yes,
yeah, of course.
Dimension, and this is like around 20 will be the
space. Even smaller in dimension 2, right?
23-dimensional manifolds. That's the 20 dimension of the 3-dimensional.
Of course, the number of parameters scale quadratically, right, with the number of coordinates, with the number of dimensions, right? So in bigger dimension, of course, we have a bigger expressiveness. But of course, again, if it scales quadratically, the dimensions of the ambient space of orders of hundreds is okay. Orders of thousands, not so okay. So for the high dimensions, you need some sparsification, or I don't know, or take some part of the coefficients of quadrics when you fit it. So it depends. But nevertheless, the algorithm as described, as described here, so it can work with any initial data, right? So it just designed that it can work effectively in big dimension and can be scaled with the number of points nicely because we're using like mini batch training. Okay, I believe that's all. Thank you for your attention. These are some references. Yeah, if you have question, I will try to answer it as much as I can. Again, I want to thank my my colleagues. Let me share another screen. This one. Yep, can you see it?
Yep.
Yeah. I want to thank my colleagues who done most of the work here. I'm just presenting the results. Yep. So this is an
better to show picture from a bar.
yeah, but that time there was no pictures, so yeah.
And show that there your faces would be considered as an outliers.
Yeah, I believe so. I believe so. It was quite nice. So definitely quite high outlier score. Yes. So we decided not to test the face recognition system and avoid taking pictures.
Okay, thank you, Fedor, once again.
Thank you.
Do we have any questions?